This is me, what we're not here to talk about. Except maybe the one thing that I've always been a nerd, hobby nerd. I think since I was 5 years old, I've done the most hopeless things with rubber bands and anything you could do with a battery. At some point, this ended up with the Commodore 64. Is any of you my generation here? With that machine, you could do amazing things if you could figure out what is going on inside this, which wasn't always that easy when you were 14 years old. Yeah, I can see the smile on your face, Mark. The reason why I'm mentioning this is because it really struck me the contrast between what we were fighting back then and what we can play with today. And imagine those 12, 14, 16-year-old kids, what they can do today, what they have to play with. And this is basically the purpose of my talk here. It is to show one of the easiest way, maybe the most easy way to do these experiments and make digital products. It started out in 2004. This student, Arando Barragan, exchange student, Colombian exchange student in Italy. The sentence I had on the previous slide was actually defining his master's thesis. He wanted to make a platform that made it so easy for everyone to make digital products. He came up with a wiring platform. And the wiring platform was the combination of some simple PCB with a microcontroller, an IDE, and some libraries to program the thing. That was modified a little bit 1 year later. A cheaper chipset, and everything was open sourced. And then Arduino was born. And by the way, the name Arduino is actually the name of the bar where the community used to meet to form the project back then. And this is what Arduino is. This is open source electronics with the complete stack around it. It's open source electronics, all software is open source. It has a huge community. I just Googled Arduino this morning and I had 24 million hits. A couple of those could be the bar in Italy, but I guess most of them is actually that platform. It has a huge community. It's being used for educational purposes at technical universities all around the world. And as I said, it's open source. And I guess all these things together is the reason why it has a huge community, and it's so easy to get started with this platform. And I know this may sound like a product presentation for this. It's not meant to be so. This is just one alternative of what is out there if you want to make digital products. But again, it's so easy to get started with this. This is how it looks like. Or so, in real shape. These boards come in 4 or 5 form factors. But this is by far the most common. And what it has, 2 rows with some connectors. The upper row, a series of digital pins for digital I/O. The lower one for analog input. Then it has a USB connector and a power connector. And this is pretty much standard. But this is open source, so there may be a lot of vendors implementing the thing. But they have to comply with the sizes and a couple of physical characteristics here. So basically, they all look the same, though another one could be red or green. Those connectors on the PCB are being used to extend the board. And you can find extensions for anything or everything here. Extensions are called shields, and you stack shields on top of each other on the board here. And when I say you can find extensions for everything, I really mean everything. And I know by saying that someone out there is trying to figure out some very exotic thing which you could not find a shield for. But you can. Trust me, there's a shield for everything in this world. When you want to program this thing, you go to the official Arduino website and you download the IDE, which looks like this. And yes, this is an IDE, but it's not, say, a rich IDE like what you're used to with Visual Studio or IntelliJ. It's more like an advanced editor with a compile button, but it works. So let's figure out how we can program this thing. Almost any Hello World program in the Arduino world is using pin number 13 on the board. The reason for this is that pin number 13 is mounted to a little lamp, a little LED. So it's very easy to see if you actually control pin number 13. We will do the same with our Hello World. This is my program. And it shows the structure of all programs, no exception, in the Arduino world. We have a setup function call, which, surprise, is being called once. And we have the loop, which is being called, even bigger surprise, over and over again. So what I do here is, in the setup, I define that pin number 13 is used for output today. In the loop, I turn it high. Wait 1 second, it goes low, and I wait 1 second, and I repeat everything. And talking about surprises, I guess it's no big surprise that this is the result. So this is our first Hello World. Let's try to extend it a little bit. On the connectors here, we have not only digital I/O, we have a couple of serial pins of a serial port, RX and TX. They can come in very handy here because the Hello Worlds that we're used to are often printing Hello World rather than just turning on something. So let's see if we can do the same thing here. This is what my program looks like now. As I said, there's no rocket science here. Those 2 pins on the board, marked RX and TX, if you don't do anything with them, they are connected to the USB port, which you use to program the thing. And the IDE has a console. So in fact, the RX and TX pins establish a connection to the console through USB. And this is what we do here. So the serial .begin actually just initializes the serial communication at a certain speed. And then in my loop, the serial print line, I print a couple of, I guess you cannot call it statements, but I print something to the console as the lamp flashes. And this is the result. Please note, in my console here, I have configured the same speed as I did for the serial communication. So what we've seen with this, or what we can take from what we've seen so far, is that the programming language is very C-like. It is C, at least to the untrained eye. I cannot say that deep down in the motor of things, there's something that breaks the C specification. But programming is C, and if you have any knowledge of C or some high-level programming language, you can do your things in the Arduino world here. If we go back to the console, it has an input field too. Let's try to use that. And this is what we do. Again, we initialize the serial communication in the loop as long as some data is available on the serial communication, we read it and we print it. So what does it do? Well, it actually just echoes. What I type in the input field is being echoed to the output field. One character at a time. Or if we do like this, one string at a time rather than one character. Which also shows that, yeah, we are programming microcontrollers here, but the language or the library availability is pretty rich here. You can actually find methods or function calls for anything. It is pretty rich. Let's move on a bit. Let's try to read an input. In the Arduino world, you don't need pull up or pull down resistors. Does everyone know what that is? No. Let's say I want to read an input on my board here. This board is being equipped with 5 volts. So high is 5, low is 0. I want to read an input, and I want to do something when the input goes high. So what I could do is just wait for the input to go high, say 5 volts on the input, and I would react to that. On the other hand, the way it works is that if the voltage on the input is close to 5 volts, 3 point something and above, it's high. And if it's close to 0, like 1 point something and lower than that, it is definitely low. But anything in between could be anything. So if I just leave the input, waiting for it to go high, I cannot really tell if its current state is high or low right now because it's just floating. So one way to deal with that is, well, I could just put a wire in the input to ground. Then it's definitely low. And now I can wait for it to go high. But if I do so, drag it to ground, and then apply 5 volts to it to let it go high, then I would effectively short-circuit things. So, no exception. Anywhere where you deal with digital inputs, and this has nothing to do with Arduino, always you use what we call pull-up and pull-down resistors. So what I do is I mount a resistor between the input and ground. Then it's, from an electrical point of view, definitely mounted to ground. But when I apply 5 volts to the thing, I don't short-circuit things because now it's high, but there's a resistor between high and low. So we call this I pull it down. Or if I want the input to be activated when it goes low, then I pull it high and wait for it to go low. We don't need to do this in the Arduino world. As I said, you always do so dealing with digital inputs. In fact, you do it so always that it has been done for you on the Arduino board. This is how it looks in code. So what I do is I say, pin number 2 should be my input today. In my setup function, third line, my input button should go high. means I want a pull-up resistor on that input. So now I can wait for it to go low, and then I can react, which is what I do in my loop. So in my loop, I say, if the input goes low, meaning someone is mounting the input to ground, I turn on my lamp. And if not, I turn off my lamp. And this just repeats over and over again. And by the way, the default clock frequency of this thing is 16 megahertz. So this is the speed of the loop here. So now we've seen digital input, digital output, and some simple serial communication. What does this do? Sometimes questions are so stupid that you do not dare to answer them. It turns on my lamp, waits 5 milliseconds, turns off, waits 5 milliseconds, and repeats the whole thing over and over again. What is the result here? The result is turn it on, turn it off, turn it on, turn it off. So on the average, it's turned halfway on all the time. And since the on and off periods are just the same, we say that we have a 50% duty cycle here. So we make square brackets on the output. And if you mount a lamp to that, as we did on pin number 13, we'll just see that the lamp is on at a lower intensity, as if it was permanently on. So this is kind of analog output that we have here. And in fact, on the board, this is supported. We call this pulse width modulation, which is supported by the hardware. A number of outputs have been marked with a tilde. Those outputs support this exact thing. And we do it like this. So I configure this, one of these outputs, for being an output. And I can turn it permanently off, permanently on, or to 50%, 10, or 90%. So the board has built-in analog output, or at least kind of analog output, to a very slow human eye. If we move to the other side of the board, there are a number of pins marked with A something. These are analog inputs. Let's try to use one of those. Which we do like this. And what do we do here? Well, I configure an input, one of the analog pins, to be an input. Actually, it cannot be anything else but an input, but still, I do it. I read the value with the analog read, which reads a value between 0 and 1023, always. And here comes a little handy utility thing in the map function. So I can map a value from a certain range into another range. And I do this here. And then I write this value to the analog output. So this little piece of software here actually reads an analog input, and the value of that is being controlled to set the level of an analog output. So, where does this take us? We've seen inputs and outputs, digital and analog. We could have done that with simple wiring too. So let's see if we can make it a bit more advanced here. This little bird's nest here mounts this component, which is a temperature sensing semiconductor. It's not a transistor, as you thought. It works that way that you take one of the pins to ground, another pin to 5 volts, and on the middle pin you can read a voltage between 0 and 5 depending on the current temperature of the thing. In software it looks like this. The interesting thing here is the read temperature function call here. So what it does is it reads the value of the pin. Remember that is a value between 0 and 1033. It converts it to the current voltage. Now I know from the specifications of this little thing that it can measure negative temperatures too, so it has an offset. And 10 millivolts corresponds to 1 degree. So I have the voltage and I convert it into a temperature, which I print to the console. I wait 5 seconds and I do the same thing over again. Result. Here we can see another thing. When I tested this thing, I tried to heaten up the thing with my fingers, which kind of succeeded. But when I released the thing again, of course it started to cool off again. We can see it ended up at 23.24, which magically was one of the values that it had before. This, of course, reflects that we have a very limited resolution when we read the input. It's only 10 bits, up to 1033. So it might, on the hardware side, be real analog input, but on the software side, it's being sampled at a pretty low resolution. Ten years ago, there was a very popular project called LCD-Proc. Did any of you play with that? You did. Huh? I don't hear. Oh, yeah. LCD-Proc was a little piece of software for your PCs that allowed you to mount a certain type of displays to your PC and then control it through a serial port or a parallel port, which were both pretty common back then. Those displays are certain type of Hitachi displays, which have become an industrial standard for LCD displays. That display we can control with the Arduino too. You can buy a lot of shields for that, so you can just mount them. In my case, I didn't use a shield, so I had to do the wiring myself, which, by the way, I brought here. The wiring is pretty simple in this case. It's basically 4 data pins, a couple of control pins to control contrast and intensity on the display, and then power supply. Let's see how it looks in software. How many lines of code do you think it takes to print hello world here? This display is so much a standard that it is supported out of the box by Arduino. It has a library to do this. So what I do is I define a variable of type liquid crystal. That structure takes some parameters, which are basically the data pins and those control pins to control the contrast and the backlight on the display. And all I need to do is then tell the size of the display, in this case, 16 columns, 2 lines. And then I can print to the display. Which looks like this. I'll just go back to the previous slide. No, let's wait with that. Sorry. Let's rather make it a bit more advanced first. So now I can read an analog input or I can convert a temperature to an analog reading that I can print, and I have a display. Let's combine the things. This is what we do here. These are just those two pieces of software that we melt together. Please note, in the loop where I define my string with the temperature, I add a space at the end of that string. This display is actually pretty intelligent. It is a real display. It's a real screen. It has a cursor. So when I print to the display, it leaves the cursor at the end. And if I print again, it will just append. So this is why I set the cursor back to position 0.0. But it could be that the string that I'm printing now is one space shorter than the one that was there before. So just to make sure that the rest of the line is being erased, this is what I do here. And this is the result. Big surprise. We're in a connected world today, so let's try to connect things that we do here. I want you to pay attention to a couple of lines here. The software serial library will become your friend when you program these things. This one works with a shield that I have here. This shield is actually a CAN bus, so it could have been used in the TomTom talk just before. But I don't use the CAN bus here, but it has a serial communication port too, on which I have mounted a GPS unit. So in fact, this is nothing but a serial port with a GPS. Let's see what we do. I configure the software serial or a variable of type software serial, which I call GPS serial, to use those 2 pins that are used to mount the GPS here. In my setup, I initialize my console. I initialize my GPS serial line, and I print something. In the loop, as long as I have something to read on the GPS serial line, I print it out to my console. Then I wait, and I do it all over again. Also, please note the tiny GPS plus line. This is actually a leftover from an experiment that I did. That may become important later on. This is the output. I don't know if any of you is familiar with the NMEA standard of GPS. Can any of you read this? Not really. I can't. I have really tried to find my coordinates here. I cannot. Let's just go back. See, I include tiny GPS at the top here, and I make a variable of tiny GPS plus called GPS. I'm using that here. So I have made a little a little function which I call wait and read. In my wait and read, I basically wait until the GPS has some data ready for me on the serial channel. And when it has, I read the characters, and those characters I give to the GPS, which was this variable of type tiny GPS from that library that I included. And I ask this variable, or this, actually it's not a real object, or this structure to encode the thing for me. And then I do some waiting, which basically just ensures that I want to read for at least that long until I'm happy. What I get here is, well, the GPS encodes my data. So in my loop, where I call the wait and read, I can take out the location from the GPS variable and print it. So rather than reading nonsense from the GPS unit, this is my output. And again, I tried to find these numbers in this mess. No, forget it. So now we have a little device that can read the position and print it. Before we move on, we need to introduce the big brother of the board that I had just before. This Arduino Yun, as it's called, it has another microcontroller. It has a microcontroller with a little Linux kernel. So it has two microcontrollers, the one that we use to what we've done so far, and then the Linux kernel. And then it actually has a network plug and Wi-Fi. Or from a schematic point of view, this is how it's built up. The important thing here is the bridge in the middle. So we have the normal Arduino and the extension, and a bridge in the middle. This is how my program looks now. I do pretty much the same thing as I did before, except I include process.h at the top. And if you look at the setup, I initialize the bridge that you just saw on the schematic drawing. In my loop, rather than printing my position, I'm calling an upload method now, a function. Then I wait for a minute and I do the thing again. And here is my upload. Because of the bridge and the process, I can actually make a Linux process now. So in the upload, I can build up a simple curl command, which I can run as a shell command in my process. So what I do here is I make a curl post with a JSON structure that contains my longitude and my latitude, and I curl it to somewhere in the world. So now, being in a connected world, I can actually upload my position, my GPS position. And I print the same thing. So it's not a very movable thing I have here, because it's kind of hooked up to my console through this. So this is a structure that it could upload. Let's figure out what else we can do. Then we need another shield. which I have here. This shield is in fact a telephone. On the back side here, you can mount a SIM card. It even has 2 jackets for earplugs and microphone. This is called a GPRS shield. Once again, the software serial library is your friend here. That one happens to define a couple of serial pins, RX and TX, which I have at the very top here. I initialize my software serial, which my GPRS variable of type software serial, at a certain speed. And as long as I can read something on the serial communication, I print it to the console. And as long as there's something, as I type something in the console, I transmit it to the GPS shield. This is what this software does. The result is that I can actually, in my console, I can type in commands to this. And the way you control this is, as you did with modems back in the days, simple AT commands. So if I type in this AT command in the middle, it would actually dial that phone number. There's a much better example on this URL here. It actually transformed this into a little call center where you can send SMS and various things from your console. And if you go to the official Arduino website, you can find examples on how you make HTTP requests with this thing. So rather than curling my structure to somewhere in the world, I could do it, say, with real HTTP with this. And when I have this, I can actually make a GPS tracker, which I have here. So here's my GPS unit, my GPS modem, and a battery here. So that one I could mount in my car or on the back of my children or whatever and follow the things. So what have we seen here? We've seen a lot of building blocks, all of them very, very simple. Digital input, output, analog input, output, GPS, network communication, which actually turned out to be just serial communication, all of it. Everything you do with Arduino is a combination of those building blocks. And when you start to combine these things, you can really do magic, like this bird's nest, which is something that I'm playing with right now. I figured out this was a bit too risky to take this on the plane, so I cannot show it to you. But what it is it's an Arduino board, it's an e-ink display. It has a little SD card reader for some extra storage and a Bluetooth thing. With that, I have an extension to my phone. So from my phone, I can send a screenshot to the e-ink display. And here's a big secret for you. I hope this could be the next generation of the conference badges. Don't tell anyone. And with these words, I'd like to thank you for being here. And don't forget to rate this session. Yeah?
Thanks everybody for asking the questions. We got quite some, Preben. The first question is, are there any more advanced IDEs for programming the Arduino, especially for debugging stuff and things like that?
Well, there's nothing more advanced than what this IDE does. There are a lot of extensions to existing IDEs that can do pretty much the same. And since it's open source everything, there are in fact a lot of alternative software. But it's not, so far I haven't seen an IntelliJ plugin for Arduino. It will come.
Yeah. Another question is, in one of your first temperature examples, you transferred the voltage to a specific temperature.
Yeah.
How would you normally go about knowing how that conversion would work, especially with different types of sensors?
Well, when I buy the sensor, I have a data sheet with the sensor. So it tells me everything, the range and the resolution and everything. It comes with a data sheet.
Okay, thank you. Another question is, how does the Arduino compare to a Raspberry Pi, for example?
The Raspberry Pi is much more advanced. That is close to being a PC.
Yeah.
This one is, well, in my opinion, much more simple. I'm very aware of that you could, with a Raspberry Pi, you can do media centers or whatever. You can do video encoding that you cannot do with an Arduino because of the computing power of things. So I think they address different areas.
Yeah.
Yeah.
You talked about, you showed us a number of shields, and you said that there is a shield for everything.
Okay, hit me.
And well, that's not a shield question, but more, how do you go about deciding which speed shield uses? Do they all run on 6900 baud or
again, there are technical specifications for every shield. So from the tech spec of my GPS modem, I knew that this one is running at 19.2. So of course, this is what I use when I initialize my serial thing. I knew the GPS is 4.8. But again, it comes with specification saying how to do it.
And how do you do it when you combine multiple shields with one solution?
Well, from a pure practical point of view, I stack the shields. Then it might be a problem if they require the same pins on the Arduino. But most often, you can actually configure the shields. So one thing may be the default choice that I used here. But you could say that, no, this shield should use pin number 9 and 10 rather than 7 and 8.
And another one is, how do you typically move from an Arduino prototype solution to a more production-ready solution? How would you do that?
Well, first of all, one thing I didn't mention is there was a picture in the beginning that showed this thing with a UPS connector, a USB connector, and a power connector. Once I have transferred my program to this thing, it stays here. So when I unplug it, it stays. So next time, I don't need a USB connector to power the thing. This is where the power connector comes in. So in this case, this is why my tracker here works with a battery. And I don't need to have a computer attached because the program is already here. So it's meant for working offline. But having said that, it is open source. And the bootloader and the software here is actually open source and is known by the IDE. The IDE has a menu point called Burn Bootloader. So you could actually take all my subcomponents here, make your own PCB, solder everything together, and then bootstrap the thing from the IDE.
Yeah, cool. And there was one really smart guy that was paying attention very well. He said, well, don't put the GPS box on the back of your children because you won't find them, because the latitude and longitude are mixed around in your solution.
Yes.
Okay, well, Preben, thank you very much for your presentation and the deep dive. Everybody, big applause for Preben.
Thank you.